Welcome back to a how-to guide prepared by the Urban Big Data Center. My name is Rafael Verduzco and I am a research associate at the University of Glasgow. Today I will introduce the second part of the multimodal transport routing tutorial for the United Kingdom with R. In part 1 of the tutorial, I introduced some basic elements for routing in the UK. In part 2, I will focus on travel time matrices, that is, estimating the travel time from several origins to several destinations. I will mention some elements about the rationale of doing this, and then I will move on to talk about the data inputs needed for this type of estimates. Also, I'll mention some advanced routing parameters that can be included for this computation. First, we will estimate some simplified travel time matrices, and then we will move on to the detailed travel time matrices. Next, we will account for travel time variability, and lastly, we will use this information to account for the nearest amenity. Travel time matrices are a central component in accessibility measures. In this formula, I am showing the specification of a generic location-based measure. This contains essentially two elements: the size of the importance of the destinations as perceived as residents or travelers. And the second one is the cost of moving or traveling from location I to destination J. Imagine we have a single origin, but we have three destinations. For this matrix, we will need to estimate the cost of traveling from origin 1 to destination 1, from origin 1 to destination 2, from origin 1 to destination 3. Thus, the size of the matrix is only 3. However, if we include two origins, the size of the matrix will increase to 9. Additionally, if we include a single additional destination and a single additional origin, the size of the matrix will increase to 16. In a real case scenario where we have, for example, let's say 1,000 zones, and we want to know the travel time distance from each origin to every possible destination, we will need to estimate a travel time matrix of 1 million. This is to illustrate the point that the size of the matrix can quickly increase. In fact, this has been the bottleneck for estimating accessibility measures, since it would take very long time to estimate this type of measures. As we did in part 1 of this tutorial, we will be using the R5R software for R. This software, it is very efficient because it uses parallel computing. That means that it can estimate the travel time from several origins to several destinations simultaneously. That substantially increases the speeds and allows the computation of very large travel time matrices. Today, we will continue using the GitHub repository, which is available in the link of these slides. We are back into our R Studio project. First, I will go to the R folder, and here I will go straight into the script number 4. This assumes that the audience already covered the contents of the previous part of the tutorial and that they successfully run the script number 3. In this second part, as I briefly mentioned, we will cover the travel time matrices. So the first thing that I will do is allocate the memory for the R5R software. In this case, it will be enough to allocate 4 gigabytes RAM. Second, I will load the R5R library, and then I will specify the directory where we created our network. In our case, this is called Scotland_router. Next, we will read the network that we created in the previous tutorial, and this just takes a few seconds. This is because we don't need to create the network every time that we want to load the data that was estimated before. Now I proceed to load the packages that I will need for this session. The next section of the code simply downloads the data or the geographic areas that we will be using as a reference for this tutorial. So this first part downloads the data zones for Scotland, as I'm doing it right now. Then I will unzip the data. We can double check that the data downloaded correctly, going to the respective folder, and the information is here. And I will also need the boundary of the Glasgow greater area, and for that reason I'm going to use the NHS health board data. So first I create a new directory within the data folder, and next I simply download the data for Scotland. Similarly, I will unzip the files, and we see that the data openly correctly. In the next section, first I'm going to read the health board boundaries defined by the NHS, and I'm going to select only the one that refers to the greater Glasgow area. This is just an intermediate step to filter the data zones that are covering the Glasgow greater area. Next, I read all the data zones for Scotland, and we see that there are about 7,000 data zones for Scotland, but we will create the centroids of each of these data zones, and then we're going to filter the centroids that fall within the definition of the greater Glasgow area. Now we see that the Glasgow centroid objects contain only 1,457 points. So those are only the centroids for the data zones that represent Glasgow greater area. And we can see an overview of the data. So each of the data zone contains the name and also some additional information as the area in square kilometers. Lastly, we will transform the ID for the data zone into a column which is actually called ID. So this is how the R5R software recognizes that this is a unique origin. And finally, I will simply plot the centroids representing the data zones within Glasgow area. Next, I will define the parameters that I will use to estimate the travel time matrix. First, the mode, which in this case is going to be a combination of walking and all the public transport modes available in our data. And also the time and date of departure, which is within the period which is covered by the GTFS information that we just downloaded. Another parameters that I will modify is the maximum duration of the journey. By default, this is 120 minutes, but I will limit it in this case for 90 minutes. Also, I will modify the walking speed to access or egress the public transport stations to 4.8 kilometers per hour, and I will limit the maximum walking times, the maximum walking time to the stations and the egress time from the stations to 15 minutes. In the next example, I will run a single travel time matrix from all the origins or each of the data zones just to a single destination. This is going to be represented by the Glasgow Royal Infirmary Hospital, and to do that I will create the location of this destination, first by setting an ID, second by defining its location with the latitude and longitude of the destination, and lastly I will transform this data frame into spatial object using the st as sf function, and specify the coordinate reference system to 4326. This time I will use a different function of the R5R package, which is called the travel time matrix. This takes similar arguments as the detailed itineraries. So it starts with the network that we created before and that we call R5R_core. And it also takes as an argument, it could take several origins. In this case, these origins are the centers of the data zones, and the destination is going to be just one in this case, which is the Glasgow Royal Infirmary. There are other arguments that we can specify, but this time we will just keep it as simple as possible. So we will run this function. I still didn't load the Royal Infirmary location, so I'll run this part of the code, and then the travel time matrix is running. So as you can see, it didn't take long. Now I have the object ready, and I can see that the dimension of this travel time matrix is 1210 rows, and it includes 3 columns. So if we see to the structure of the data, we will see that we have 3 columns. The first one contains the ID of the origins, and the second contains the ID of the destination. The third column simply contains the estimated travel time between this specific origin and that destination. We will see that the name of the column is travel time, the percentile 50, and as you might remember from the previous tutorial, we said that we can compute travel time windows within a specific range. So if we compute different travel time windows, then R5R will return the median travel time. So let's say that if it compute 10 different travel times, then it will return the median travel time. In this map, we can see a representation of the travel time it takes to go by public transport from each of the data zones in Greater Glasgow to this location, which is the Glasgow Royal Infirmary Hospital. Additionally, in the next section, we can estimate an expanded travel time matrix. As you saw from the previous travel time matrix, this contains just very simple information about the route that was estimated from one origin to one destination. So if we use the expanded travel time matrix function within the R5R package, then we can obtain additional information. In this case, I am using very similar arguments as I did before, but in this case, I am using an additional argument which sets the breakdown to true. So in a moment, you will see that this parameter is doing to our results. So our travel time matrix is ready. And now if we look at the dimension of this travel time matrix, we will see that we have similar number of rows, but now we have 12 columns. So if we look at the contents of these different columns, we will see that we have additional information. So now we have the origins in one column and the IDs of the destination in the next column. And we also have detailed information, for example, about how long it took to access the public transport service. So for example, to go from this origin to this destination, departing at 8 in the morning, it took 2.8 minutes. The waiting time to board the public transport vehicle was almost 18 minutes, and the ride time on, or the time on board on the public transport vehicle, was almost 40 minutes. And the transfer time in this journey was about 3 minutes. And finally, the egress time of this journey was about 12 minutes. In this case, the number of public transport vehicles rode was 2, and it actually tells us the ID that it's contained in the GTFS files of the public transport services that were used in this journey. And of course, it also gives us the total time estimated for this journey. So using this information, we can also visualize and get more information about the public transport system that we are analyzing. So in this case, for example, I am visualizing the number of rides that it takes to get from each data zone in Greater Glasgow to the Glasgow Royal Infirmary Hospital. So of course that we see that in nearby areas, the number of rides is 0 because they simply walk, but we can also see some patterns of the number, regarding the number of rides that the people or the resident needs to travel to this destination by public transport. And these are basically representing train stations that are linking the data zones to this destination. We can also visualize the waiting time, for example, and we can see that the waiting time is very heterogeneous, and that might tell us something about the frequency of the service of the public transport in different zones. We can also visualize the access egress time that it takes to board or to reach the final destination of the location that we're estimating. It took some time to plot, but there we go. We have plotted the access time to go to the closest public transport station and the egress time, that is the walking time that it took from the last public transport station to reach the final destination. In this section of the script, we're going to estimate all-to-all travel time matrix, and that is from all of the data zones in Glasgow, or each of the data zones in Glasgow, to all of the acute hospitals in Greater Glasgow. First, I'll get some data about the hospital's location, and then I'll get some of their characteristics, and later I will simply filter the location of these amenities. In the last step, I will transform the data to a simple data frame as a spatial object, and I will filter the locations that fall within the Greater Glasgow Area Health Board. Another important element that I haven't mentioned in this tutorial is that we need to specify the geographic coordinates as latitude, longitude. This is why I need to transfer from the coordinate reference system used in the UK to the latitude, longitude coordinates. And the last thing, I will rename the location column in the hospital's dataset to the ID, as this is required by the R5R package. In this all-to-all travel time matrix, I will set a time window of 30 minutes. So that means that as I set the time of departure at 8 a.m., we will cover a time window between 8 in the morning to 8:30 in the morning. And I will also define the percentiles to be the 25 percentile, 50 percentile, and 75 percentile. If you remember in the example before, the output only provided the median travel time for the travel time estimated in that time window, but we can also obtain additional information. This time I will use the travel time matrix function, and here I can also specify the percentiles that I want to retrieve from this travel time matrix. Also, I'm specifying the time window in which I want to estimate the travel time by public transport. In my machine, this took about 1 or 2 minutes, and it was a little bit longer than the other matrices, since remember that we are estimating several origins to several destinations, but we are also considering different departure times within a time window. So if we look at these, at the dimensions of the output, we will see that we have about 12,000 rows and we have 5 columns. If we look at the contents of the output, we will see that the information is organized in a sparse matrix format, where we have the origin ID in the first column. Then we have the ID of the destination in the second column. And we will have the different estimates of the travel time. Next, we can use this travel time matrix to find the nearest hospital from each of the data zones. To do that, I will group from the origin of the travel time matrix, and I will summarize by finding the minimum travel time using the percentile, the 25 percentile, 50 percentile, and 75 percentile. So if we compute a summary, we will see that for the lowest percentile, the maximum travel time and as well as the medium time is shorter than the 50th percentile, and similarly for the 75 percentile. For example, we see here that the median travel time to the nearest hospital is slightly longer than for the other estimates. The reason for this is because the 25 percentile estimates the trips that are available only under 1/4 of the travel time window that we defined. So it means that these travel times are available only during a fraction of our time window. By contrast, if we look at the travel time which reports the 75 percentile, this reflects the travel time which is available during a longer period, and that is during at least 3/4 of the time window that we define. That is between 8 in the morning and 8:30 in the morning. Now we can plot this information according to the different travel time percentiles, and I will enlarge the view of this map. In these maps, we can see the nearest distance to a hospital from all data zones in Glasgow. And we can see this visualization represented by the different travel time percentiles computed. And we can see some slight differences between the maps. So for example, we can see that the percentile 25, which is available only during 1/4 of the time window, is representing, or it is producing larger catchment, slightly larger catchment areas compared to the travel time where the percentile is 50, and that means that the travel times estimated are available at least during half of the time window that we defined. Usually these travel times would be useful to represent different types of travelers. For example, the travel time percentile of 25 would be a traveler with flexible time. So those are, for example, travelers that just show up and ride, while the percentile 25 is representing travelers who plan their trip ahead. That is, travelers who might look at the public transport time schedule and reduce their waiting time. This is the end of the part 2 of the tutorial and the end of the how-to guide. We believe that by using the resources and the materials that we have provided, the audience can easily extend and customize the analysis to their own area of study. Thank you very much for watching, and we hope to see you in our next how-to guide.